fact, I just bumped into somebody in the hallway earlier, and we ended up talking about it, and he had a very different perspective on the whole talk than I did. That just happens because we had a collective experience and we're walking around.
Okay, let's start. So first of all, I want to say thank you everyone for coming and choosing my talk. There are so many great talks in this conference, and you choosing and being here in this big room, I'm amazed. Thank you very much for coming. Few words about myself. I'm Dathskovsky. I have more than 17 years of system programming. I did a lot of different systems, from medical systems that save lives to security systems that take life. You have to do both, you know. I work in a company that's called Speed Data. We are a great startup, and we are developing the next big thing in big data. So basically what we are doing is we are creating a new CPU, a general purpose CPU that will accelerate your analytics by a lot. And maybe in CppCon next year, I will finally have a chip, and I will do something about the chip, finally. I have a LinkedIn, so there I speak a lot about C++, things, riddles, things that people hate. And if you want to join there, you can do that. That's going to be really great if you just follow me. I started a blog because LinkedIn is just small posts, and I wanted to post more and explain more that people would understand. So CPP Next, that's a site that I started. And I have a YouTube channel. I already have 7 videos. So after this talk, go like and subscribe. I would appreciate it a lot, but not now, right? And now we can start with toInt or toUint. What can you expect from this talk? So first of all, I want to say it's not going to be a talk, it's going to be a rant, me ranting about C++ and how horrible all those rules about ints and uints are. And it's not made for people. So we have to understand those types to really appreciate them and really understand what they're doing to our program. Any of you ever started looking at these types and just like, how would I say it? The first thing that comes to your mind when you do it is just putting an int everywhere, right? Put your hands if you're thinking about integers. Int. I don't know if it's wrong or right, but it's a problem. Our mindset is like from school is going to int, and it's not always the right type for the job. So we will talk about that. I will show you many pitfalls of what can happen if you select the wrong type. Bad things can happen. There could be undefined behavior. There are so many small rules that it's pretty amazing how can you fall with the simplest thing in the language. So let's start. And I selected to start with quotes for unknown people. For here we have Bjarne, which is an anonymous person in C++. Nobody knows him, right? So Bjarne is saying there are far too many integral types. There are far too many lenient rules to understand how to work with them. And he is saying basically from all this is stay simple. Always use signed types. Is he right? We will see. Then we have Dale. Dale is a very known blogger. He works at NVIDIA. He uses integral types a lot with graphics and floating point types. And he is basically saying something totally different. He's saying you don't have to use signed integers. You almost never have to use signed integers. Indexes, sizes, everything is unsigned. So why is our mental state is saying always use an integer? It's not always correct. So he is saying stop using that, use only unsigned types. Is he correct? I'm not sure about that as well. So just for you to understand, this talk is not going to be controversial. You will not get of it like use only this type. This is not the point of it. The point is for you to understand the importance of the selection for the correct integral type, that something so simple can be so complicated. And there is a disclaimer. Everything I'm going to show you will be compiled for x86. Each machine has a different ISA, and it works a little bit different. I selected x86 because most of you probably use x86, right? Someone works on something that is not x86? Some people, okay. But most of you use x86, so it's going to be beneficial for most of you to understand the machine that you are using. And most of the compilation will be done with Clang 12. And the reason for that? Wait for it. And to get us started, let's start with a simple example. For a simple function, basically two functions. One is for unsigned integers, one is for signed integers. All this function is doing is receiving two parameters, signed or unsigned, but the same type. It's doing a sum of A and B, and then divides it by 2. Same functionality, different type. Now I want to see hands. Who thinks that the unsigned version will be faster? Better assembly, faster runtimes? Almost no one. Signed, who thinks the signed will be better? You think both will be the same. Okay, 2. The signed one will be better. Okay, let's try to look at it. And of course, let's try and start with the disassembly of the first unsigned version. Already we can see that the assembly for this is pretty simple. 3 lines of code. That's amazing. Now, for this talk, you will have to understand x86 assembly a little bit, but don't worry, I will teach you some assembly. First thing that you need to know that x86 machines have registers. They have different size registers, and they're built with 8-bit registers, 16-bit registers, and so on until 64-bit registers. And that is because it has historical reasons. They just built the processor one on top of the other. So they started with 8 bits and went to 64 bits, which is the standard right now. But you have all of those inside your machine today. The most important thing, just to understand the code, is to see that things that start with R are the 64-bit registers. Things that start with E and have 3 letters are the 32-bit registers. Other things will not be covered so much, so you will be fine. And if you want to know more about this, you can see Dave Sinkel's very good talk from CPP Now 2023, Under the Hood. So I think it's going to be very beneficial for everyone to understand how those things work. Now let's start. The first instruction from this disassembly is LEA. LEA is an instruction that said load effective address. This instruction doesn't load an effective address. This instruction is basically used to calculate and speed up calculation for registers. So as you can see, instead of using 2 add instructions, the compiler could generate this instruction with RDI plus RSI with one assembler code line. So that's cool. And you can even use more registers in the same instruction. I don't have those here, but you can. And the compiler actually generates those things. The next thing is shift right. No division here, a shift. And then we just return. Anyone can say why shift and not division? We will talk about it, but I want to see if you understand. Sorry? Yes, but we will understand why it's faster as well. Okay, now let's look at the signed version. Ta-da! It's bigger and it's slower. Not by that much, but still it has more assembly code lines. And if we will start looking at it, we can see it does the same thing with the LEA. It still loads the effective address. But then it does something peculiar. It takes a copy from the sum that it just did and copies it to RAX. Then it shifts 63 bits and basically extracting the most significant bit from the number. Then it adds this most significant bit to the RAX, to the summation that we already done in the first line. And then it uses shift arithmetical right, which is weird, right? But what happened here? Because the code, the compiler knows that you are doing division by 2, the compiler knows that it can accelerate it for you because division by 2 is the same as shifting right. And shifting right is faster. Again, we will get why it's faster. We have to understand, for that we have to understand that each instruction, it's fetched from the memory and pushed into a pipeline. And inside that pipeline, it has an execution stage. And inside that execution stage, some execution operation have pipes as well. So we have 2 pipes inside our pipeline. There's a limited number of units in your CPU. So you have to understand that sometimes you will stall because you don't have the units available. And each instruction has its own latency. Now, what is latency? In very, very simple definition here, latency is the number of cycles that it takes the processor to compute your instruction or your opcode. Of course, if you have errors, misalignments, and cache misses, it will be slower. If it's a cache miss, you have to go to the memory, you will stall, it will take more time. If you have an error, you will have to recover from the error, so the cycle count will go up. Surprisingly, nones and infinities do not increase your latency. And here is a good example of why division is not selected. So our baseline is add. Add is a very simple ALU instruction. It's not pipe, and therefore it has just 1 cycle. It takes 1 cycle to calculate addition. IMUL is a multiplication of integral types. It takes 3 cycles. Again, it's very dependent on the CPU that you have, but it takes somehow 3 cycles. Division takes at least 20 times more than the multiplication. And it depends on your architecture. It can be worse. So that's why it almost never, if the compiler can select something else and not division, it will select it. If you can help the compiler and do something by yourself, it will be even greater. Here I just want to explain how the pipelines that I talked about, how they work. So you have a pipeline. By the way, this is a super simplistic pipeline that doesn't work like that anymore. The pipelines in x86 right now are much more aggressive than this. This is a joke. But for us to understand how pipelines work, that's good enough. So in this simplistic pipeline, we have 4 stages. The first stage is fetching from the memory. The second stage is decoding, understanding the registers that we will use. And then we have the execution part. And then we need to write back because we want to store the result somewhere, right? And if everything, all stars are aligned, you will have a bandwidth of 1 instruction per cycle. How great is that? But usually it doesn't work that way. So if you have an instruction that stalls for some reason, for example, like here, it tries to access the memory, and it takes a lot of time to access the memory. But then you have instructions that don't actually use what we are trying to copy from the memory. They are getting stalled for no reason. And then you don't get your 1 instruction per cycle anymore. And that's a problem. But the good thing is that our new processors already know what to do with it. There's something that's called out-of-order execution. It basically says if you don't have hazards between those instructions, then you can just execute them all together and then reorder them to make it seem like it was ran in a sequential way. So it's pretty cool. And if you want to learn more about it, you can see my talk about C++ memory model from last year. And if you would like to hear the extended version, then I did one in CPP now. I went more into memory ordering there. So compilers and CPUs are good for you. They are your friends. They are trying to make things better and run faster for you. You shouldn't be scared of them. You should understand how they work. And hopefully after this talk, you will understand it better. Let's get back to the example. So, right, we know that we have latency, and that's why we selected shift. But here we had to add another shift, and then we are using shift arithmetical right. And to understand why we are doing that, we need to understand the difference between signed and unsigned integers, how they are stored in your memory. Unsigned integers are represented as modulo 2. They support only positive numbers. Overflow is well defined. And that is very important for our talk, that overflow for unsigned ints is well defined. The range is very, very big. As you can see, it's 2 in the power of n, and it can represent only zeros because only positive numbers. To represent an unsigned integer, you have to have the bits. For example, here we have 1, 0, 1, 1, 0. Then you have weights. The weights are basically 2 in the power of the index for the bit. And then if you want to represent it in decimal, you will have to do a multiplication of the bit with the weight, and then to sum everything together. And here we are basically representing 22. Overflow is defined like in discrete math. Who remembers discrete math? Cool. So it's the same. Basically, it's the same for unsigned ints. It's like looking at a clock. So if the clock is now at 11 a.m. and we want to add 2 hours to it, so the clock will overflow to 1 p.m. The same happens here, basically. If we have 4-bit integers that are represented from 0 to 15, if we are at 15 right now and we want to add 2 to it, it's defined. We will just overflow to 1. So that's good. Signed integers, on the other hand, they support both types. They support negative numbers as well. They are stored using 3 different types, so it was defined by the compiler how they would store it. Signed in magnitude, 1's complement and 2's complement. We will get to what happened in C++ in a minute. Overflow is considered to be undefined behavior. We don't know what it is. And the range, of course, is from negative numbers to positive numbers, but the number that can be represented are smaller because we have to have the negative numbers and the bit is already taken. 1's complement. Let me take you back to school. So 1's complement is a very easy way to represent a negative number, or basically a signed integer. To do that, all you have to do is to take all the bits. You have to look at the number that you are seeing. You have to look at it as if it's an assigned integer and flip all the bits. The problem with 1's complement is if you will look at 7, we have rubbish there. So 7, if we will flip all the bits, we will get 0. And then we will get -0. And that means that we will represent less numbers and we'll just represent something that is not important to anyone. And this is an example of 15. We have all 1's. We will look at them as if they are unsigned. Then we're flipping everything, and we get -0, which we cannot do anything with. 2's complement is almost the same, almost the same. But the only difference is that we are taking the same flip of the bits, and then we're adding 1 to it. Because we are adding the 1 to it, we can represent more numbers. We don't have the rubbish anymore. So if we look at 7 right now, it will be -1. And it's a representation that we do want. And as you can see, the representation of the numbers looks even better now. And again, a simple example with 15. We flip all the bits. We add 1 to those bits. And we get -1. Simple, and this representation is better for everyone. That's why in C++20 it finally was standardized. Compilers cannot choose anymore. Newer compilers have to implement it with 2's complement, which is good. And another thing that is important to remember, that positive numbers are represented exactly the same as if they were unsigned. Now let's get back to our example. So we understand maybe why we had to do that, but the important part is here is the SIR. SIR, as I mentioned, it's shift arithmetical right. So now we have to understand what is the difference between SIR and SHR, logical and arithmetical. Logical shift right, what it does is it pushes all your bit right, and then most significant bit will be 0. With shift arithmetical right, it does the same thing, but it will keep the most significant bit lead if it was 1. So shift arithmetical right is the correct way to go for unsigned integers. That's why the compiler selected SAR and not SHL. But still, we don't understand why we had to extract the most significant bit, or basically the signest bit, and add it to the number that we got before. And only then we shift. So why have we needed to do that? Yeah.
To interrupt, but I think the comparison is not really fair because like you are comparing two different implementations. Because for unsigned integer, like for signed integer, the functionality is not really the same, because for negative integer, if we divide it by 2, we will like it will act as if we like plus 1 then divide by 2 if it's an odd number, right?
And
so
it's still the same. It's still an integral type. You still have to do some rounding.
I mean, like for example, if the compiler know the two integers are positive, or their sum is positive, then it will generate the same assembly as if.
But it cannot know that.
My point is, because the compiler do not know, it's because we are comparing two different functions. Like
we are comparing, no, I don't agree with it. We are comparing almost the same function with different types. Yes, that's why you get different assembler code, but the functionality is the same.
No, their their functionality is same. If you you are comparing apples and two oranges, I think.
No, it's not correct. I'm sorry, but it's not. It's the same functionality with different types. It does the same thing, but a little bit differently because the compiler and the processor needs to process it differently. I'm sorry, I have to run. You can talk to me later. Let's continue. So now, why did we have to do the shift right and extract the bit from it? And that's again because the only difference that I didn't mention about shift arithmetical right and shift logical right is that the rounding mode is different. Shift logical right is it's rounding to 0, and shift arithmetic right is rounding to nearest. And that's why it needs to extract the bit, because the rounding is not the same. To get the same rounding, it has to add the 1 to it. If it's unsigned, because you need to round to a different place. And that's basically it. You can understand that even the simplest example is not as simple as you think when you're using different types. It's just different integral types and you have different outcomes. The logic is the same. The code that you get is different. And if we would look at the performance, because the performance is not that different here, because we had almost the same code that was generated, it's a little bit faster than the signed type. The unsigned. It's a little bit faster, but not by too much. The point here is just to understand that there is a difference between those two. Now that we understood a little bit more about signed and unsigned, we can talk about the pitfalls of using both of them together. And this is the interactive part. So here I would ask you to be more interactive with me if you can. So we have a very simple function that takes two unsigned ints in the size of 8 bits. It returns something that is auto, and it just adds them together. That's it. What will happen if we call this function with 255 unsigned and 1 unsigned. What will be the result of this function? Whoever yelled that is correct. Who thought it's going to be 0? Let's see why it's not 0. So let's be a compiler for a second. If we are looking at the compiler, because the types that we used were uint8, and they are smaller than the integer type, no matter what it is, it has to be promoted to int, to a signed int. Not even unsigned, it just promoted to signed int. And then because we are used auto, the compiler says, hey, your return type is int. And you get 256. You thought it's going to be 0, you thought it's going to overflow, but no. Now let's look at almost the same function, but here the return type is concrete. We're saying we want to get uint8 back. And of course, here, if we will do the same thing, the compiler will just add a narrowing of the type back. So it created an int, it added those, but then it narrowed it back to unsigned char. And then, of course, we will get 0. Let's look at another function. This function is totally auto. So you return an auto type, you get an auto type, x and y, and you just add those two. Pretty simple. So now I want to add them with those types. I want to do it with 1, which is unsigned int 64, and minus 2, which is signed int 64. What will be the result here? The result here will be problematic. Because we gave it signed and unsigned types, the signed type will be promoted to be unsigned type. And then you will just add 2 unsigned types together, and you will return an unsigned type. And that means that you will get this number. Not what you thought it's going to be. You thought it's going to be -1 maybe, but no. Another quick example is a silly code that does a count. It receives uint64, size in, it creates a local variable, and then it runs in a for loop from 0, but then our primal mind says, yeah, it's a for, let's put an int. But size is unsigned. So what happens here is that I will be promoted to be unsigned, and then this loop will run forever. This is an endless loop. It will be UB as well. Yep. I don't hear you, I'm sorry. Oh yeah, good catch, thank you. Okay, another thing that might happen with those things is like, look at this function. We were smart enough to say if it's 0, we will do nothing. And if it's not 0, we will create a buffer of 255 bytes. And then we will run in a loop. But again, someone decided to select an int and not an unsigned int for size. And because we selected in the for loop an unsigned int, because we thought it's going to be better, it's never going to be something that is negative, it will be promoted again, and you will have an overflow, buffer overflow here. If someone was, by mistake even, if someone will provide -1, it's an overflow. Just to make it clear, all those little code snippets are from actual code bases. People write it. I'm not making these things up. And this example and this pattern appears more and more, and it makes me angrier and angrier every day. People think that auto is really cool. I think auto is cool, but you don't have to use it everywhere. And if you don't understand exactly what assigning a 0 to an auto will do, you're creating a monster here. So what will be the type of I? Sorry? Integer. But size is not integer. So again, we have all this thing with promotions to unsigned int. It's a problem, and people do that. It's a good thing to use literals, because literals are constant, but you have to understand that we have a lot of literals in the language. And if you want to use and to be smart and to use the correct thing with auto, you have to understand what will happen if you assign it with the auto. So here I have an example of A1 to 6, and each one of those will be something different. The compiler decides it's an int, unsigned int, long, unsigned long, 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 and unsigned long, long. You have to understand those things to actually use the auto there. Who knows about size t? Nice. Who knows why size t was created? Okay. So size t is just an unsigned integer. It's used for size operations. It's defined in CSTD def. It has max int size. It's introduced in C89, long time ago. And it was introduced for fixing the portability problem. The portability problem was that basically sometimes unsigned int wasn't enough to represent all the memory, and unsigned long was too big to represent the memory. So you just lost a lot of room in the memory for nothing. So it was implemented for this, and it's portable. So in each system, it's a different size, and then you represent yourself correctly. In POSIX 1 2017, we got something that's called S size t. It's almost the same as size t. It's not standardized. It's standardized in POSIX. And it means it does the same thing, but at least it can represent -1 as well. It's beneficial in many cases. And in my opinion, like this code snippet that will be available in C++23, I don't remember, so don't catch me for the word. In C++20, we already have a function stood as size to do that. But basically what I wanted to do here, and we cannot do it now because all the containers have size, and size is unsigned, and if I'm subtracting 1 from it, it will create a monster, and it will create almost an endless loop for us. With S size, if this vector is 0, then we will not loop, and we will not run. So it's pretty neat. I think it's one of the good examples for that usage, and there were a lot of talks about it in the standard as well. And in C++23, we got more literals. We got the Z literal and the UZ literal, which is basically S size t and size t literal. And on my system, it's long and unsigned long. Pop quiz, everyone. So play with me here. This is a very simple function that receives a 64-bit unsigned integer. It uses modulus 64 on it, and then it shifts left on 1. What can happen here? Hands, anyone? Yeah? Can you come to the microphone, please?
One is int, typically 32 bits, so you could be overshifting.
Thank you. That's exactly the answer. So again, someone here didn't understand what literals are in C++. And he or she used the incorrect literal type here and basically created undefined behavior. So you have to be very, very careful when you use those types. Now after we understand the pitfalls and what are signed and unsigned integer, how they are represented in the memory, we can actually go and look at something that it's a little bit more complex than what we just seen. So I want to show you something that sums up an arithmetic series. An arithmetic series is basically a series of numbers that has a constant difference between each 2 consecutive numbers. So 1 to n, it's an arithmetic series. To calculate the sum of the arithmetic series, we have a very clean and nice equation that just does a1 plus an, which is the first element plus the last element, multiplied by the number of elements divided by 2. Pretty simple. And if we will look at the C++ code, again, I have 2 functions. One function is using only unsigned types, the other function using only signed types, but they are doing the same thing. They're just running in a loop and adding to sum. Nothing special. And the numbers cannot be negative, of course. All the numbers here are positive. So logically, they are the same. Who thinks unsigned will be faster? Who thinks signed will be faster? Almost the same number of people. So that's interesting. Let's look at the code, of course. Let's look at the disassembly. So the disassembly for the unsigned one is not that bad. It's not that bad. The first thing we are doing is testing, and basically test is just setting a flag for JE, jump equal, if RDI is 0. If RDI is 0, basically we receive the size of 0, and we have to do nothing. Then we jump here, and we're using a very, very fancy zeroing method that's called XOR, and we're just zeroing it out and returning AX. But if it's not 0, that means we have work to do. We're initializing ECX with 1, then we're zeroing AEX, and then we're jumping into a loop. We're adding RAX and RCX, that's basically we're adding the sum. We're incrementing the index. Then we're checking if the index already got to what we need, and if it's below or equal, it will jump back to the loop. As you know, loops are not performant. There's a lot of things that you have to do with branching that you don't want to do them in this case. But still, the compiler created a loop here. If we will look at the signed version, we can see that those two blocks are the same for unsigned. Nothing changed. But if we look at this block, it's basically this equation. We will not go into the code because it's a little bit more complex, but the compiler understood that it can use the equation and it doesn't need to loop. Nice. And if we will look at the performance here, the signed version is 40 times faster than the unsigned version. Can anyone guess why? Microphone.
Because for unsigned integer, overflow is defined behavior, so it must to handle it.
Thank you. So yeah, it's undefined behavior. We just took something bad and leveraged it for ourselves, and undefined behavior is undefined behavior. It just says that the compiler can do whatever it wants. So most of the times, not always, the compiler says, hey, it cannot happen. So if it cannot happen, I will do whatever I want. And it just adds it, and it may overflow. So it will work 1,000 times, but then it will fail on the 1,001 time. And if you will change your compiler, it acts differently. It's undefined behavior. So don't leverage undefined behavior. And here we are getting to the section, so what shall we do? We want performance in our program, but we want the program to be well-defined. And in this day and age when our government is sending notes and telling C++ is very bad, don't use C++, we cannot use undefined behavior for our advantage. So we have to always try and to create programs that are well-defined and used correctly. And this is maybe the most important part of all this presentation. It's how to make your code a little bit safer. So first thing is, if right now you are not using these flags in your build system, go to your DevOps team or to your build team or whatever and tell them, we need those flags. If you are not using these flags, it masks a lot of things that the compilers just say, it's not that bad. You won't see warnings for a comparison of signed and unsigned types. You won't see overflows. You won't see anything. But if you will use that, first, it will be really, really painful because you will have to fix all the problems that you have. But after you fix those problems, it's a better and safer code. Warnings, to me, are errors. You shouldn't have a warning in your system. And I see many systems that just ignore error warnings. And I come to companies and they are showing me, this is how we compile. And then I see like 300 warnings. And I say, are you sure your code works fine? And they have tons of undefined behavior. And they just don't see it. So closing your eyes doesn't help, especially in a language that is so unsafe. So let's be safer. And that's just an example of what we will get. So x is an unsigned integer, and minus 10 is an integer. Your compiler will just tell you, hey, you're doing something wrong. I will do something that might harm you, so please fix it. If you really want to do it like that, you will have to do something with it. To do a static cast on it by yourself, to do reentry cuffs with Launder, something, but not leave it like that. Use newer compilers if you can. Newer compilers almost always fix their bugs and the performance gets better. It almost always brings new bugs, and then the undefined behaviors that you leveraged because they worked stopped working right now, and you have to fix those. So me as a compiler developer, I fight a lot with these things, but usually after you fix your code, the performance gets better, much better. And in our case, I compiled this with Clang 17 instead of Clang 12, and we get the same performance for the arithmetic series. Same performance, not 40 times faster or slower, they are the same now. And this is the code. So you can see there are no loops here. The code for a signed version is still UB. But the code for the signed version, it just uses a couple of little instructions. So the difference is almost unnoticeable. The compilers are getting better. Another thing that I would suggest is using these flags. Who's seen those flags before? Who uses those flags? One person? Wow. 2. 3. There is some usage. Those are great. They are basically saying, I am not allowing you to do overflow anymore. If there is an overflow, I will catch it for you. And the most amazing thing with those flags, there is almost no performance hit in release mode. So you can use them, and it will not hit you. Your program will be safer. Another addition to the standard is fast-n. Fast-n integers are just a way to say to the compiler, I don't care what type you will use, what integral type you will use. All I know, I need it to be unsigned or signed. You select the size for me. Select the size that will be the best in performance. And the compiler does it for you. And usually the compiler does a better job than you. So usually when I see people using the sized versions, they almost always use Uint 64, int 64. Is it better for everything? Maybe not. Leverage those things. You have to understand your CPU. So we talked a lot about x86, but there are different CPUs. I work with ARM and RISC-V and our own CPU, so each one of those CPUs has different ISAs, they have different behaviors, they promise different things. So if you work on a project and you work in C++, at least know the CPU you are working on. You have to understand what are the risks or what are the promises from that CPU vendor, what you're going to get. And don't be afraid to look at assembly code. As you've seen, it's not that bad. We went through a lot of assembly, and I showed you assembly for x86, which is the most horrible assembly in the world. It's the hardest to read. RISC-V and ARM are much, much easier. So don't be afraid to do that. You will just learn a lot about your programs. Another good thing is in C++11, you got new helpers. There's a make signed helper and a make unsigned helper. What those helpers do is basically taking a type you are requesting and returning the signed or unsigned type depending on the helper. So it looks something like that. If we have a function that takes in an auto, it can be anything, and returns anything, And inside that function, all we ask is make sign t. We're taking the decal type of val, so it's some kind of type. Let's say it's unsigned. And we are providing it with the val itself. So what it will do, it will take the type, create a type that is the best match with signed, and just initialize it for you. And if we will look at the examples downstairs, it's basically, I'm creating it with Uint 10t, with 10. Then I'm checking that I'm actually getting a type that is const int64, const because we use the literal, so it is a const type. And then I'm checking that it's still 10, and it is. So if you use mixed types, those helpers will be very beneficial for you to use. If you have ability to use C++20, those functions are amazing. Basically, those are safe comparison functions for mixed types. So if you want to use mixed types, and you know that sometimes you use mixed types in your system, those functions will do the job for you. They promise you that they will do the correct thing for you, and they will not do something unexpected, unlike if you are writing the code for yourself. So to show you how that works is we have a function that always returns int64. It receives two parameters, x and y. It has an if that checks if x is lesser than y, then we return y. If not, we return x. Basically, it's a very simplistic max function. And if we will use this function with -10, which is an integer, and 20ul, which is an unsigned integer, what will we get? -10. Because -10 will be promoted. And because it is promoted, it is a larger number than 20. And because it's larger, -10 wins. Not really max. All you have to do is to use this function. Just compare less. And if you will use this function, and we will call the same function with the same parameters, you will get 20. Exactly what you wanted. And we are using mixed types here. How cool. Simple, readable, and does the work safely. The most important part is safely. I cannot stress this more. Don't use auto just because it's cool. I love auto. I use it a lot because I'm a generic programmer. I use a lot of template metaprogramming. And I use it because I need it. But to use it just without a reason, that's problematic, at least. That is bug prone, and you might burn with a bug that you will have to debug for like days just because you used auto for something that you don't understand exactly what you're doing. Try to use concrete types as much as you can. I showed you a function where it's not generic and someone tried to put auto there. Why? You know exactly the types you are working on. Why not to put the types that you need? Why to be cool? Not always. You don't always have to be that. Safety is an important part. Use more than loops as much as you can. Index-based loops are, someone said that they are a source of all evil already, or is it just me? Let's say it's just me. Okay, with indexed loops, you can overflow, you can do the incorrect things, you can mix and match types. They are problematic. But if you will use the correct for each or range-based loops or ranges, you will get what you need, and it will not be unsafe. And the last thing is strong types. Use strong types as much as you can. Strong types will not create the problems that we've seen. If you want to use integer for price, for example, create a price. Don't use just an integer, because you will get implicit conversions all over if you will use integer. And this is something that I actually seen, not with this name, but someone actually approached me and said, hey, I created a strong integer. No, you did not. You created an alias to an integer and you will get the same problems that you get with an integer. So don't do that and don't think it is a strong type. If you want to create a strong type, do it like this. There are many different ways to create a strong type. You don't actually have to do it exactly like this, but I like this because it uses an explicit constructor that says that I know what I am. I will not do implicit conversions for you. You have to know who you are, and that is just great and safe. So this is the way to go. And if you take anything from this talk, I would like you to take that C++ can be safe. You just need to understand it. And even the most simplistic part in C++ can be really, really harmful. And so you have to understand the things that you are doing. You have to be certain, and you have to be curious. Learn your assembly, understand what you're doing, learn the standard, and you will be safe and performant. So we got to the end. Thank you very much. If you have questions, please.
Also, if I can I continue my my question in the first place about the a plus b divided by 2 thing. So the reason I say they are different is because logically they are different. Because for signed integer, for the first function, it's not simply as a plus b divided by 2 in math. Because it's actually more like if a plus b is larger than 0, then we return a plus b divided by 2 floor.
No.
Then,
and again, you need to look at the assembly code. The compiler is doing exactly what you're saying, and that's why you have a different code.
No. I mean, there is a else. Else, we are doing a plus b ceiling. So but for unsigned integer, we are always doing a plus b divided by 2. If suppose that all the integer are even... Again, no, I'm sorry, no. You always have the rounding mode. You always round. So because you're using integral types, you round. It always will be a seal or a floor. It depends on the system, but it always used it. And you can see, because it's used shift, logical, or arithmetical, it has to do something to get the rounding mode correct. I mean, for example, if we assert all the integers are positive, even with the first implementation, it will generate the same code. It's generating different code because it has to handle a case that you do not need to handle for unsigned integer. The reason it has to handle another case is because it's mathematically different. For unsigned integer, the formula is a plus b divided by 2 floor, and for signed integer, it's a plus b divided by 2 floor only if a plus b is non-negative. If it's negative, then the formula changed. It's now a plus b divided by 2 ceiling.
But I'm not trying to say it's not what you're saying. I'm trying to say it's exactly what you say. You just need to understand if you use signed or unsigned, you will get something different. That is exactly the point. So people don't think that. They think it's just functionally different. And they don't understand that the code that will be generated is a little bit different. And you've seen that. You understand it mathematically, and that's great. But you always have to keep it in your mind to understand what you're doing. That's exactly what this talk was about. Understand what you're doing. Don't put just an integral type because you want to put an integral type. Don't put int everywhere. If you know it will always be unsigned, you know that it's never going to be less than 0, don't use it. That's exactly the point.
But we can also achieve this by, for example, asserting.
Sorry, come for me later.
Could you show the slide with the max function?
The ceiling max function.
Or the
this one?
The compare. So you're basically saying that writing different arguments makes it safe or unsafe. To me, it seems like it's basically pushing the unsafety around, because fundamentally, if you call it with U long max and -1, there is no right answer. And you just decide how you're going to fail.
I agree with that totally. But what I'm trying to say is basically, sometimes people write code totally bad. And like, if you will not use this function, you will crash and burn in a worse way than with this function. At least this function will give you the correct-ish answer.
Okay, fair enough.
Yes, David.
So I think that when you say C++ is safe as long as you know how to use it is a little bit misleading. It's kind of like saying, hey, it's totally safe to drive without a seatbelt and crash through windows and all that kind of stuff. As long as you just are careful while you're driving, I think that what you've demonstrated very well is that C++ is not safe at all, because who the hell is going to learn all these rules before they start actually writing code in production? Like, you're saying like, okay, you know, anybody can do open heart surgery as long as you know how to do it, right?
It's not the same argument.
The answer to the less than problem in C++ is we made some obscure library, this obscure call in this other header, which Elias and I, we're both in the standardization committee, we're like, we didn't know about this thing. If that's the answer to that problem, like, C++ is not safe, and it's not getting any safer as far as I can. So, anyway.
David, so I cannot argue with that. I cannot.
Of course.
What I'm trying to say is, don't use Rust. That's all I'm saying.
that would be a mistake.
Hi. So yeah, my question is along the same lines. If we feel we have a function which is better than just a comparison operator, why haven't we overloaded the comparison operator for the type?
Backward compatibility. First of all, it's just got in C++20. So people use the regular operators. You cannot just remove those. And some people take advantage of undefined behavior in C++. Apparently, I heard. And if you will take that away, they will kill you, because they say, hey, my program runs so fast, and now you killed it. Even logically, it will do something different. So if they wrote something bad and they are depending on that bad thing, that's their own fault. And they will stay with that bad thing forever, because it's legacy code. We will not touch legacy code. No one, if Peter is here, maybe he touches legacy code, but that's the only person in the world.
Okay, thank you.
Anyone else? Oh, yeah. Oh, sorry, please.
Great talk. I just had one question. So when you, there was a slide where you said that the unsigned int was 40 times slower than int. I didn't totally understand why.
Undefined behavior. Because signed ints don't define overflows, the compiler just said it cannot happen. And the compilers do it a lot. And because it cannot happen, I can do whatever I want. I just can use this neat equation and everything will be fine and dandy. So it was faster. Most of the times it will work. Sometimes not.
Okay, thank you.
Welcome. Yes?
Very practical question. Say, I store a bunch of numbers that I use to index a vector. And so what should they be? Int, uint, size t. The guidelines say don't use unsigned, use signed. Don't use any arithmetic on that.
It really depends. It's like a hard question to answer. As you've seen during the talk, I used that and I used that. So for me, it's the right weapon for the job. So if you need something to be unsigned for some reason, signed, use signed. I showed an example that with a very simple function that uses SIT, you can get something really neat and clean your code. So if you need something like that, do that. It's hard for me to say exactly what to use. It really depends.
Well, but it is a very simple use case, just to index.
Indexes to what? To a vector?
Yes.
Just indexes to a vector? I would go with unsigned.
Thank you.
You're welcome. But that's me. Yes.
So the thing with indexing, though, is you might subtract the indices, and you might index a pointer, and you can index a pointer by negative numbers.
Right. You're right. So yeah, integers. Because of the p difference. He's right. Thank you. And if we don't have any more questions, we're out of time. So thank you very much for coming.